3.2. Introducing the notion of confidence interval for a mean. 3.2.1. When sigma is known. Suppose that for all I, xi follows our normal distribution with mean equal to mu, and variance equal to sigma square. Then if you standardize the data, you get the following formula. From that formula, you can easily deduce a confidence interval for mu, where u index 1 minus alpha divided by 2 is the quantile of a normal distribution x, such as the probability that x is lower than u index 1 minus alpha divided by 2 is equal to 1 minus alpha divided by 2. You should read the formula this way. Or even more generally, where blah blah is the estimator of your parameter of interest, and c is a constant. 3.2.2. When sigma is not known. In this situation, the standardization is not as trivial as in the previous case. You can't divide by sigma anymore, as you don't know its value. You have to estimate it in an inferential context. This word, inferential, is super important. It means that you want to generalize what you observed on the individuals of your sample, to the individuals of the whole population. In other words, as you don't know sigma, you have to estimate it, but in a particular way, that takes into account the fact that you are working with a sample. In an inferential context, we are going to use the following formula. Why so? Actually, the main idea behind that estimator is that if you work on a sample in an inferential context, you will always underestimate the variance with the sum of squares divided by n, as there is always some variability that you will miss. You observe less diversity on a sample than on the whole population. So, if you want to infer, you have to boost the formula by dividing your sum of squares by n-1, rather than by dividing by n, as s prime is a random variable, and not a constant. The distribution of the standardized x bar n is more complex than in the previous case. Hence, the confidence interval for mu is where t n-1, index 1 minus alpha divided by 2, is the quantile of a student distribution t with n-1 degrees of freedom, such as the probability that t is lower than t n-1, index 1 minus alpha divided by 2, is equal to 1 minus alpha divided by 2. In the following exercise, let's see what happens for the confidence interval of the mean when the population is finite. In the following exercise, let's see how you can get a confidence interval for a variance.